Okay guys, today what we're going to be talking about is gravity and satellites. So we have just covered uniform circular motion, and luckily, or you'll be glad to know, that gravity and satellites is just another very specific version of uniform circular motion. So before we were talking about things like friction and tension, maybe, but providing a centripetal force which causes centripetal acceleration, which makes things go in a circle uniformly. Here we're actually using the force of gravity, and in this case we actually talk about satellites. So when I'm talking about satellites, I'm not just talking about, you know, GPS and weather satellites. I'm also talking about planets and moons acting as satellites because they're orbiting something else. So in this section we can look at the forces that are actually involved here. So you can remember, hopefully you can remember Newton's third law. Newton's third law says that for every force there's an equal and opposite force, or action and reaction. Every action there's an equal and opposite reaction, so there's two forces at play between any two objects. So if I have a planet like this and I have a smaller one like this, the forces between these two things are actually the same size. So this guy applies a force of that much, this one applies a force of that much, and if you draw them better than me, you'll actually have them same length and opposite directions, so you can really obviously see that they are equal and opposite forces. This one here should also be coming from the centre, because these forces act as if they're coming from the centre of the spherical object. The next thing that I want to talk to you about is this inverse square law. So for this section of the course we actually have a really clever formula. It's Newton's law of universal gravitation. The force is equal to G, Newton's gravitational constant, not the 9.8 thing, M1, M2, masses of object 1 and 2, divided by the square of the distance between them. Now the really cool thing about this is if I increase the mass of one of these objects, so let's say I double that one, what I'm actually doing is doubling the force. So if that's on the top line, so if I double that one, I double that one. However, this inverse square law, I'm going to annoy you a little bit with it now because it comes up when we deal with electric fields as well, and a little bit to do with energy. The force is proportional to 1 over r squared. So if we imagine that all of this stuff on the top line stays the same, we can kind of imagine that that's in a black box. It's just some sort of number. It's not going to be the same. It's not going to change. So for G is a constant, so that's not going to change. M1, one of the planets isn't changing, neither is the other. But if we shift the distance between them, that's what's going to change the force. Because it's squared, we have to square the impact as well. So if I double the distance, so I'm doubling r, what I'm actually going to do is I'm doubling the 1 on r squared sort of thing. So this guy here, because it's, you know, twice as much, I'm doubling the 1 on r squared, which means the overall impact is a change by 4. So if this gets bigger, the force of attraction is going to get smaller. So if I double my distance, I've actually got a quarter of the force. Works with magnets too. If you think about it, you bring magnets close together, the force of attraction gets bigger. So if I actually double the distance, making them further apart, the force is smaller. Conversely, if I halve the distance, I'm actually squaring the halving as well, which makes it actually 4 times stronger. So I want you to, when you see these things, the inverse square laws, I want you to imagine 2s and 4s and 3s and 9s, and yeah, I'm on the right wavelength here, 4 and 16, 5 and 25, etc, etc. So if I make it a quarter the distance, so a quarter the distance is actually 16 times stronger, a fifth the distance, 25 times stronger, and so on and so on. Those pairs go together. Alright, the last part is a way to relate the centripetal force, which is where we're coming from with the uniform circular motion, and gravity and satellites. So satellites all go in orbits. These orbits are supposed to be circular. They're generally elliptical for planets in orbit and satellites that orbit the Earth, they're generally elliptical too. If I just stick with this, and we're talking perfect circles, so remember magic physics land, F equals G m1 m2 on r squared. This is a force. This is the force that provides centripetal force, the centripetal acceleration. So this guy comes back, mv squared on r. So if I've got a force that's the same, so in this case the gravitational force, which is this one, actually provides the centripetal force, I can actually say that these two things are now the same. Alright, one of the cool things we can do with this is work out, calculate the mass of planets if we want to, work out the distance between them, but more importantly we can actually show that the speed of a satellite is given by this equation. And you'll notice that m1 is the planet, I guess, at the centre of the orbit. So what we're actually looking at is a satellite in orbit. Doesn't actually matter what its mass is. All we care about is how fast it's going and how far away it is. For every speed of orbit, there's a perfectly unique radius of orbit, and that means that you can have your planet with satellites all the way around it, and these things won't run into each other because they're all, even if they're all the same radius, they've all got to be going the same speed, so they all keep getting out of each other's way. We can do a couple of other really cool things with this. What I want you to think about is a geostationary satellite. So a geostationary satellite is above a fixed point on the equator all the time. So geo means Earth, stationary, not moving. It's above one fixed point on the Earth all the time. Going back to the speed of an object going in a circle, v is 2 pi r on t. This guy here is the same as this guy here. So this is any object going in a circle. This is a satellite. It's going in a circle. These two things are the same. So what you guys need to do, and hopefully show me by next time you see me, is work out an expression for the radius in terms of the orbital period, Newton's gravitational constant. I don't want to give you too many hints. Actually, I'll just leave it as that. Alright, so what I want you to do is unite these two things. The v will disappear because these two things are the same, and actually come out with an expression r equals something. And that something can be used to calculate the radius of orbit of any sort of satellite, geostationary ones, or remember the other kind is a polar one which orbits the poles. So North and South Pole. Alright, so two things I want you to do now. I want you to come up with the expression for the geostationary satellite, and then I want you to use that to tell me the orbital period for the ISS, which is about 400k above Earth. Alright, so the radius isn't 400k's, the radius is going to be 400k's above Earth. Another little hint, radius of the Earth, 6380k's. Orbital period for one of these geostationary satellites, 86,400 seconds. It's a day, so that's 24 hours. Alright, yeah, let me know how you get on.